So this week is going to be an exciting week. We're going to do some, hopefully we get the Gauss-Bonnet theorem done this week. We'll see. We're either going to do it or get very close. And so the setup, so the context that we need to be able to prove the Gauss-Bonnet theorem is, well, first we're going to prove the Gauss-Bonnet theorem for a disk. So sure, you can have some surface over here, and this surface could have some topology or whatever. But right now, what we're going to do is imagine we have a coordinate chart. That coordinate chart has some image, right? X of u comma v, mapping into three-dimensional space here. And so that coordinate chart covers some section of your surface here, M2, sitting inside of R3. And imagine, really what we're going to do is you can imagine a disk in here. I won't draw it right now, but imagine something that's topologically a disk, right? That also would be a disk over here. And so we're really going to prove theorems in a single coordinate chart. Okay, and that's why it has to be a disk. And one thing we can do is, y'all remember that at each point over here we have, you got the I and j directions here. We could label this the partial derivative in the u direction. That's the partial derivative in the v direction. Various symbols you could use for that. And that point might map over here, for example, and then these vectors get pushed forward over here to xu and xv. And they don't have to have this length 1, by the way. These vectors here have length 1. These vectors here could have any length, and the angle between them doesn't have to be 90 degrees either. And that's xu and xv. But let's go ahead and assume that they are perpendicular. Okay. It's just for convenience. Okay. So suppose we choose a coordinate chart. They're not necessarily length 1. That's xu. That's xv. And let's go ahead and assume that they're perpendicular. Now, what is that equivalent to doing? What we're basically doing is we're going to assume that f equals 0. Right? In other words, that xu dot xv equals 0. And remember all of our formulas for k and the geodesic curvature, they all assumed f equals 0 too. It's just a handy-dandy thing. You can choose any coordinate chart you want. So it's sort of like, it just says, look, technically we could rework everything we're about to do when f is not equal to 0, but let's just choose f equal to 0. It's convenient. At latitude and longitude have f equal to 0, right? Lines of latitude are perpendicular to lines of longitude, right? And it's always possible to choose coordinate charts with f equal to 0. There's still quite a few coordinate charts you could choose. Okay, and now we know that the length of this vector here is the square root of e, right? Because xu dot xu is e, and the length of this vector is the square root of g. And so what we get then is an orthonormal basis. At each point P here, and the orthonormal basis is xu divided by the square root of e, comma xv divided by the square root of g, and then comma u. Remember what capital U is? U is the vector. These two span the tangent plane, and then you got u coming out of the board. Okay. I won't draw u. Clutter up the picture a little bit. Okay, but this is an orthonormal basis for R3 at the point P. Or for the tangent plane of R3 at point P. Okay. And so because of that, we can, what we want to do is we want to understand, hey, given a vector, let's see here. I'm making the decision to deviate from my notes just a little bit. Okay, so I always have to make an important decision. Okay, but so given a vector v, some direction, right? Say it's a tangent vector at the point P, I can take the covariant derivative of E1. I should just follow the book, okay? It's some tangent vector v, but what is a tangent vector? Imagine you have some curve, right? This is your point P here, right? imagine you have some curve, right? We call this curve alpha of t. We'll call this point P here as alpha of 0, right? P equals alpha of 0. And then at that point, that tangent vector in the direction of the curve is alpha prime of 0, right? And so imagine we're taking the derivative. We want to take the derivative of, oh, sorry. Got label things. So these vectors here, we can call this E1. That's the vector E1. This vector here is E2, and this is still U. Okay, so that equals that, that equals that. Okay, so we have these script E1 and script E2. Okay, so this is our orthonormal frame or basis at every point. And so what we want to understand is, so imagine this sort of orthonormal frame, and it's defined everywhere. It's perpendicular, but it kind of is twisting around, right? And we want to understand how it's twisting around. And so what we can do then is say, all right, let's just compute the covariant derivative of these vectors. What is the covariant derivative and the direction of some curve, alpha prime here, of E1? What does that equal? Okay. And also, while we're at it, what is the covariant derivative and the direction of your curve, alpha prime of 0, let's say, of E2? What does that equal? And in both cases, I can tell you that it's a vector, right? It's a vector. It's a three-dimensional vector. And this is an orthonormal basis, so therefore it's going to be, we use the same term we've used before, it's so many E1 plus so many E2 plus so many U in both cases, right? Now we just have to find the coefficients. Fair enough? Sorry if this thing's in the way.
Why are we doing this?
Because we want to understand how the frame is twisting around as you move along a curve.
Okay.
We're just trying, I mean, it's just a question you might ask.
Mm-hmm.
So much of mathematics is you just ask a random question. Most questions aren't that interesting, but you ask them anyway, and just by sheer dumb luck, eventually you ask an interesting question. Okay, it is a quantity thing. Now, with experience, and after you've asked 1,000 dumb questions, you start to get good at figuring out which ones are more likely to be interesting questions. But this is a natural question to ask, like how much is this orthonormal frame twisting around? It's a reasonable, or it turns out to be a very good question, right? It seems like a reasonable question, but it turns out it's going to give us the Gauss-Bonnet theorem, ultimately. And who knew? By the way, so many great breakthroughs in mathematics come from asking questions that didn't seem all that interesting at the time. It just turns out, that was the right question. Okay, so then the question we're asking here sounds rather mundane, which is what are these coefficients here, right? It's sort of like the Frenet formulas, right? I just want to see, how this frame E1, E2, this orthonormal frame. So I'll draw the picture again. So we have our surface here, and at each point you've got a frame, right? That's like E1, E2, right? And then over here it's twisted a little bit, right? And then over here it's maybe twisted a little more, right? And we're just kind of wondering, how much is it twisting as I move along some curve? That's all. Reasonable question, right? And so we don't know what to call these things. By the way, I should put R3 here. Just to point out, this is your usual three-dimensional covariant derivative. Okay? It's your usual three-dimensional, this is multivariable calculus, which you learned in multivariable calculus. Okay? Well, remember our trick? We use this trick all the time. 1 is equal to E1 dot product E1, right? So now if we take the derivative along alpha prime, right? Then we get, alpha prime applied to 1. The directional derivative of 1, of course, that's going to be 0, right? And then over here what we get is, we get the product rule, and so we get twice E1 dot product the covariant derivative and the alpha prime direction of E1. And then you're like, oh, look at this. This vector here is perpendicular to that vector there because the dot product is 0. They're perpendicular, right? Which means that the coefficient of E1 here, right, with itself, this is a 0 here. 0 times E1. right? And that's actually, by the way, the rate of change of E1, you can rotate this way, you can rotate that way, but you can't rotate that way. Right? You get what I'm saying? You can only rotate E1 in the E2 direction, either plus E2 or negative E2, right? And so this is actually makes sense intuitively as well. So we have a zero, rate of change of E1 is 0 E1 component, and the rate of change of E2 for the same reason has 0 E2 component as well. So we've got zeros there. And to follow the book a little bit more, just to introduce some notation, let me do this. We know it's going to be 0, but let me introduce notation now, because notation, frankly, is somewhat approximately half of differential geometry to understand what the words and the symbols mean. That's what it always seemed like to me. So they came up with these coefficients. They call this omega 1, 1. They call this omega 1, 2. Make sure I get that. Yeah, no, they call it 2, 1. Sorry. The 2 comes from here, and the 1 comes from there. And then they call this S1, I think. And then I call this omega 1, 2. Remember, the first number comes from the E, and this number comes from here. And then plus omega 2, 2. And then they call this S2. That's their notation, okay? Yeah, and do it some. You know, see this, the subscripts all over the place? It gets worse. But on the other hand, that's a lot better than A, B, C, D, E, F, G, or the alphabet or something like that. You might as well number things way better than using letters, right? Like even us using U and V, really we should use U1, U2, right? Because what if I want to go to the third dimension? Then I can just do U1, U2, U3, right? So much easier. Okay. And what we realize now is that this W1 here is 0. So this is 0, so I can erase this whole thing here, right? And then this W2 is 0, so I can erase this whole thing here. And not only that, we have a second example of our trick, which is, remember that E1, E2 have 0 dot product, so this is our trick again, right? 0 equals E1 dot product E2, right? And now take the derivative along alpha, and so you get 0 equals the directional derivative along the curve alpha prime. And then when I apply it here, this is going to be E1, dot product, the derivative, covariant derivative along alpha of E2 plus the covariant derivative along alpha 1 of E1 dot product E2, right? Yeah, sorry about all the erasing. Plus. Okay, you just see the product rule there, right? And so what this is saying, when you work this out, E1 dot product, the derivative of E2, derivative of E2 is here, dot product E1, that's W1, 2 here, right? W1, 2. And then, but then the derivative of E1 dot product E2, that's W2, 1. And so what you see is that these actually add up to 0. So they're equal but opposite. One is the negative of the other, right? So if you know the one, you know the other. And so how about this? Instead of writing W1, 2, we can just call that as negative W2, 1. Okay, so this is the long and the short of it. That's what we get out of it. And so I don't even need to call this W1, 2 here. I can just call this negative. By the way, it's omega 2, 1. I usually, when I said W, I meant omega. So omega is in the book. It's the Greek letter for W. Okay. And then you can say, well, what is, so let's just summarize kind of what we have then. Is that the covariant derivative, now let's do the covariant derivative on the surface M. Okay, this is your surface M2. So I'm going to drop the R3. Okay. Now, what is that defined to be? It's defined to be everything except for the normal component. It's defined to be the tangential component of the covariant derivative. I think we defined that a couple of weeks ago before spring break, didn't we? Or did we? Maybe it's been a while. I don't remember, did we? Well, let me just define it again just to make sure. Maybe we didn't. The covariant derivative of one vector field and the direction of another vector field, this is going to be defined to be just the tangential part of the R3. So this is what you learned from your multivariable calculus class, okay? Multivariable calculus, okay? And you just take the part that's in the tangent plane, the part that the ant can understand, okay? And so we'll call this the covariant derivative. This is the intrinsic covariant derivative. Maybe we did not define this yet. Yeah, I think we defined this. This was just your multivariable covariant derivative. I think we used the term covariant derivative for this. But then the ant cannot understand this. If you start talking about the third dimension, the ant's blind, right? The ant knows two dimensions, forward and backwards, left and right. The ant doesn't know about this third dimension because they don't have eyes. They have no way to perceive it. And so, okay, if we want to talk to the ant, right, we have to throw away the S1U and the S2U here. We just throw that away. And it turns out it makes sense to take it's well defined to take the tangential part. Okay? And so in this case, for example, the covariant derivative along the curve alpha prime of E1 therefore is equal to omega 2,1. By the way, of alpha prime, because this omega 2,1, that coefficient depends on the direction you're going, right? Times E2. And the covariant derivative along the curve in the direction alpha prime of E2 is negative omega 2,1 of alpha prime times E1. Okay. And so this is the intrinsic covariant derivative formulas. Okay, it's just a definition. It's just a definition. Now,
Sorry.
Yes.
I just want to so the multivariable calculus.
mhm.
So is that just kind of a gradient with respect to x that we're taking there? Or what is?
Yeah. So what this is, just a right.
Yeah. Or-
This is equal to when I say this. I'll just remind you what this is. X and Y are vector fields.
Right.
Y has components. Okay, just let me write this down first. Y1, comma, Y2, comma, Y3. That's what Y is. And then what you do is you take the directional derivative of each of the components
Right.
using X. This is what we did in class.
Right.
Yeah. And by the way, you did that in your multivariable calculus class too. You just didn't call it the covariant derivative.
Oh, okay.
I mean, it's just look. If I said take the derivative, if you think of y as three functions, I say they take the directional derivative of y as three functions. This is what you get, right? What else would it be? Right. So if I never taught you anything and I said take the directional derivative of y in the direction of some vector field x, this is what you would write down, right? Okay, and it turns out that's correct when you're on R3. When you're on a surface and you want to talk about the intrinsic covariant derivative, you do exactly the same thing, it's just you throw away the normal components. Okay?
Okay. Okay.
Now here's the thing that is remarkable. I'm about to tell you something that's really quite surprising, and I'm not going to prove it right now because it's way too hard to prove right now. Okay? But I'm about to tell you something remarkable. This definition of intrinsic covariant derivative, the ant is unable to do that computation, right? Because it says first figure out the R3 derivative and then take the tangential component. So the ant is like, what the hell are you talking about? Third dimension, what? But a sufficiently clever ant who's sufficiently knowledgeable about Math 421 can figure out a different definition that does make sense in his world. All right, that's actually, there is a formula in terms of things he understands. All right, and here's the shocker. You ready for this? It's actually quite a complicated formula. No, it's not easy. Okay, it's actually hard. Believe it or not, it's called the Levi-Civita formula, and I'll show it to you in a few weeks. But let me just point out that it's not particularly intuitive. It was really quite hard. I don't think, if I gave it as a challenge problem to you guys to figure it out yourself, it'd be a little bit of a dirty trick. It's not really possible. I mean, it would take quite a bit of ingenuity, and I'd be extremely impressed. No one figures this out themselves. Everyone has to be shown it. All right. Obviously, Levi Civita figured it out. So but even there, how do people figure things out? Sometimes they just get lucky, right? They're just dorking around and they tried this, they tried that. Next thing you know, they have a formula, right? And they're like, what's that? And they don't even understand what they have when they have it. And then someone else explains it to them, and then in hindsight, oh yeah, look, I'm the genius. I figured this out, right? But they weren't even trying to solve that problem when they solved it half the time, right? That's actually quite common, right? So when you think about the hundreds of years and the centuries, and in some cases millennia, that people have been thinking about problems, and the thousands of people and tens of thousands of people who've been thinking about them, if not more, right? It's just a huge amount of effort has gone into just randomly trying every possible thought, right? And so we get this accumulated wisdom. And so accumulated wisdom allows us to see that this intrinsic covariant derivative is in fact computable by the ant. It really truly is an intrinsic covariant derivative, okay? But right now all I can do is define it this way. And this is why, and certainly let's put it this way. This definition seems like a plausible definition. If you give the ant a vector field y and a vector field x and say, hey, what's the rate of change of this vector field y in the direction of x, right? The ant would eventually come up with something, right? And it turns out and then on the other hand, we could speculate, well, maybe the correct answer is just take the tangential part of this, right? But and guess what? It turns out that is right. Whatever makes sense to the ant and makes sense to us to tell the ant, also they end up being the same. By the way, I say it would be a dirty trick for you to try to figure out the Levi-Civita formula for this. Or it would be a great joy, but just to be prepared to spend a lot of time. That's all I'm saying. Of course you could do it eventually, right? It's just a matter of how much time do you have. It would take a long time. If someone, by the way, just to give just a comment on that real quick, when you guys do your theses, if you go to graduate school, I mean, if you run into a problem like this, yeah, of course you could do it. If you took 3 years, of course you could do it, right? But you don't want to just spend 3 years randomly, right? Or yeah, you could probably do it in months, actually, a focused concentration, I would think. Maybe you could do it in a weekend. Who knows? It's easier just to look it up. And then it's like a really elegant, beautiful thing, which I will show you in 2 or 3 weeks. Okay. So ultimately, we have this new object here. It's this thing right here, right? This is telling us how much. It's a number. This omega 2(1) is a number, a real number, and it's telling us how the rate at which our frame is rotating along some curve. Right? It's telling us something about the rate at which it's rotating. And so, for example, another thing we can do is we can say, what does this allows us to do? There's a couple of things we can do. One is the notion of a parallel vector field. So applications, parallel vector fields. Okay, the simplest example of a parallel vector field would be a bunch of parallel lines in three-dimensional space, okay? So the name, it's reasonably well named. What we're really looking for are constant vector fields, okay? But what would be a parallel vector field on a curved space? That's a different question, right? And so imagine you're on a sphere, for example. And you take this, again, we want to talk about vector fields that are tangent to the sphere. Okay, so we're really going to focus on intrinsic geometry here. So imagine I have this vector right here, okay? Let's see here. Actually, let me have it coming out of the board, pointing towards me, okay? So it's pointing straight at me, okay? Pointing this way, okay, out of the board. And now imagine I walk straight down to the equator, right? And I'm walking along this curve from the North Pole down to the equator, and I start out and I'm pointing in the direction of the vector field. And I say I want to define a constant vector field along this path. And I just point that way, and I'm walking in a straight line. And when I get here, I'm now pointing that way. Fair enough? I'm pointing down. In the 3 dimensions, it's pointing down as opposed to level, right? And so I walk down to the equator. I'm pointing this way. And then someone says, now I want you to walk along the equator to this point over here, 90 degrees along the equator, to this point. So that's the third point over here. And when I do that, and they're like, but don't change the direction you're pointing. So I was like, I want it to be a constant vector field, right? So I just walk from North Pole down to the equator, right? And then someone says, walk over there. I'm like, okay, so keep constant vector field. So I'm going to turn, but I'm not turning my vector, right? Keep it pointing the same way. And now I'm going to walk along the equator. And then so as I do that, then when I get over here, this vector field is still pointing down, right? And then I say, okay, now I want you to walk back up to the North Pole. And so, let's see here. You get back like this, and then someone says, okay, now go back to the North Pole. I turn like this, now the vector is pointing opposite direction I'm going, right? And I walk all the way back up, and now this vector is going this way. So what happened is the vector, it was constant the whole time, right? But it kind of rotated on me, right? I tried to define a constant vector field, but I couldn't. Right? I mean, it was constant along the curve, but when I got back, it actually rotated by 90 degrees, didn't it?
There's like a cool way to demonstrate this with your arm. Have you ever seen it? Where you karate chop on the table.
Uh-huh.
You say, keep your wrists straight.
Yeah.
And you bend your elbow like this.
Uh-huh.
And then you bend your elbow like that. And you bend your elbow like that. And apparently without moving your wrist, your hand is going flat.
Okay, cool. So it's demonstrating the same general principle somehow. I noticed your finger was tracing out a quarter of a sphere, right?
Right.
Yeah, cool. Yeah, exactly. And so this is called holonomy. All right, is how much do curves rotate when you go along a path? Okay, and more generally, this is called a parallel vector field. This vector field here that we translate around, this is called a parallel vector field, and the angle it rotated is the holonomy of a curve. And it turns out that if it rotates one vector by 90 degrees, it rotates every vector. It doesn't matter which way you were pointing originally. It just rotates all of them the same amount. Okay? Now, why is that? Let me tell you the definition of a parallel vector field. We'll say that V is parallel along alpha of t if the covariant derivative along the curve alpha prime of t for all values of t of v is equal to 0. Okay? So in other words, if you make the vector field constant as far as the ant can tell, then we call that a parallel vector field along the curve alpha. Okay? Now, if it's a parallel vector field, observe this. There's a couple of things that are true. First of all, d dt of the length of v squared, right? This will turns out to be d dt of v dot v, right? Because v dot v is the length of v squared. And then when you apply, we say d dt, we're really taking the derivative along the curve. So this is the same thing as saying taking the directional. By the way, this is if we think of v as a function of t, right? Then it's this. But when we think of it as a function of x, y, and z, we're really taking the directional derivative along the curve alpha prime of v dot v. Okay, so this is really just a change of variables, right? And we've discussed this before. Let me not get into details again, right? But if you think it's a function of t, it's this. If you think of it as functions of x, y, and z, then you're going in that direction. Okay? So it's just a change of variables. In both cases, you're taking the derivative of the same thing along the curve, right? And so what you get then here is you get 2v dot product, the covariant derivative of an alpha prime direction of v. Okay. But now here is an interesting thing right there. Okay. Is this actually true? Well, certainly I want to point out that if we had an R3 here, that's definitely true. Would you guys agree? Because that's just your usual product rule. If I put an R3 there, right, then this is a multivariable calculus. But v is a tangent vector, so the third dimension of this doesn't make any difference when you're dot producting with a tangent vector. Do you guys get this? This is a tangent vector. If I put in a normal component here, a u, any amount of u's, dot product v is 0 anyway. So I can erase that R3 there. I can just use the intrinsic covariant derivative, and it doesn't change the value. Fair enough? So the product rule is still true for the ant. Okay? And but by definition, this is 0, so this is 0. And so the rate of change of the length of the vector is 0. I mean, the length square isn't changing, so its length isn't changing. Okay, so when you parallel translate a vector field by this definition right here, right, the length does not change. The other interesting thing is that angles do not change either. So this is one fact. The second fact is, what is d dt of, let's say, v dot w? Okay, and then this is also alpha prime of v dot w, and then you apply the product rule, so you get covariant derivative and the alpha prime direction of v dot w plus v dot the covariant derivative and the alpha prime direction of w, right? Just a product rule. And the point is, let's say you parallel translate both of them. Okay? So let's say that v and w are both parallel, then those terms are both 0 if v and w are both parallel. Okay? So the dot product does not change. So in other words, suppose I start at the North Pole and I take two vectors, right? And I'm saying this is v and that's w, and I want to make them constant along this curve. And I start walking and I keep track of both vectors, right? The point is the dot product between those two vectors does not change. The length of those vectors does not change. The dot product between doesn't change. Y'all remember the formula? V dot w equals length v length w times the cosine of the angle between them, right? You have two vectors, theta, right? Well, the dot product isn't changing, the length isn't changing, so therefore the angle between them isn't changing. And that's kind of obvious, right? Like if I'm pointing, right, if I'm keeping them both constant, I shouldn't be going like this relative to each other, right? I mean, whatever they do, they should have the same angle, and so we've proved that mathematically. Okay, so the angle between vector fields does not change. Okay. And so what that means is this holonomy of a curve, if you give me a curve, if one of them rotates by a certain amount, they all rotate by that same amount, because the angle between them isn't changing. Question?
I was going to say, is this holonomy like a measurable quantity? Like is
yes.
We assign a number to that?
Yeah, so for this curve here, the curve that starts here, and so holonomy of a closed curve. Well, yeah, a closed curve would be typically what you would talk about. You have to check the book to see if it has to be closed. But certainly if you go around a loop, right? The point is, these curves have rotated. I mean, these vectors have rotated by some amount. So you give me any closed loop, there's some number associated, like 90 degrees in this case. That's how much things rotate. And by the way, whenever you get non-zero holonomy, then you detect a curvature. Because this would not be the case on flat space, right? Remember I said a parallel vector field would just like it. If you're in R2, a flat vector field, if you're on a flat metric on R2, take any curve, right? The parallel vector field just never rotates. It never changes, right? This is only interesting when you're on a curved space. On any flat space, the holonomy of any curve is 0. This phenomenon only happens on curved spaces. Agreed? Yes?
Could you start with two parallel vectors, and then once you're done with the closed loop thing, the angle of rotation is same but it's in different direction?
No, because Greg, let's see here. Your point is this only gets angled up to a sign, right?
Yeah.
But I guess to prove it, what I would do is say take. So first of all, your question forces us to appreciate the idea that we might not be on an orientable manifold, right? So we need to. So by the way, I'm assuming that you're bounding a disk. When I say it detects curvature, if you bound a disk, it detects curvature. Okay. If you have topology, that's a whole different thing, right? Then you're either detecting topology or curvature or something non-standard, right? But assuming you're on orientable manifold, and let's just go ahead and assume it bounds a disk, right? I could start by parallel translating two perpendicular curves, call them E1, E2, right? And then they have to stay perpendicular. And then E1, E2, since they have to stay perpendicular, if one rotates 10 degrees, the other one has to rotate 10 degrees the same way as so as to stay perpendicular to that one, right? And then do things as linear combinations. So it turns out what you really have is just a rotation of the tangent plane. The tangent plane maps to itself, and it gets rotated, in this case, by 90 degrees. Yeah, so you can, I'll let you all flesh out the details. Other questions? Now let's go ahead and use some ordinary differential equations and this setup here to actually prove that parallel vector fields exist. Okay, so I'll erase these tricks here. So theorem. So this is theorem 6.5.2. By the way, we'll do this theorem. I don't present every single theorem. Y'all should read every theorem, make sure you understand them, and I suppose technically you're responsible for all theorems in the book in the sections that I assign homework on. Okay. So make sure that you study them as much as you can. I don't have time to go over every single one. I'm focusing more on the concepts, but it's good to practice your proofs. And so the theorem here says that if you have a curve, let's say it starts at the point P and ends at the point Q, and we'll call this curve alpha of t, and this P equals alpha of A, and this Q equals alpha of B, then given some vector V naught here, then there exists a parallel vector field V along the curve. Okay, so this vector field here is called V, such that so their point is given alpha of t and V naught and some initial curve, there exists, that's the backwards E, right? A vector field V defined along alpha of t such that V is a parallel vector field. Sorry, if you're taking notes, you're really mad right now. There exists a parallel vector field. Along alpha with V defined at alpha of 0 to be V naught. V equal to V naught, at the point P. Okay, so this is an existence theorem. That given an initial vector, you can do this whole thing. I was just sort of hand waving, really. Like I said, point in that direction, and okay, that was my initial definition. Then I said, oh, it's some vector field that satisfies this property. Well, how do you know there exists a vector field that satisfies this property, right? And it looks a little bit like a differential equation. In fact, we can turn it exactly into a differential equation. So proof. What we do is suppose that you have some coordinate chart that contains the whole thing, okay? So this here's our alpha t. It's in some coordinate chart. And so what that means is this E1, E2 actually forms a basis for the tangent plane everywhere, right? And so that means is I can let V equal cosine theta. By the way, sorry. Without loss of generality, let's have the length of V naught equal to 1. Okay, now why are we going to do that? If it has length 0, what's the 0 vector, then the answer is just the 0 vector everywhere, okay? If I just define V to be 0 everywhere, then covariant derivative of 0 is 0, so that's kind of trivial. If it has any other length, divide by its length. If it has length 5, divide by 5, so it has length 1. Okay? And then apply the theorem. I'm going to prove it for length 1 vectors, and then just take that answer and multiply through by 5, and that will give you the correct answer. Okay, so I'll let you check that. So without loss of generality, might as well assume that V naught equals 1. In which case, what this means then is that we can think of our vector field that we're trying to solve for, V along the curve. We can think of it as basically some rotation of E1. And if you rotate E1 by theta, you get this. Okay? You may recognize that. That's cosine theta comma sine theta parameterizes a circle. And so if I have an E1 and E2, if I go up an angle theta here, right? The angle there is theta. The vector I've drawn, in fact, is cosine theta E1 plus sine theta E2. Fair enough? And in fact, any unit vector is going to be this for some theta, right? Because all the unit vectors are on this circle here, right? And so just pick up the theta that corresponds to the unit vector you're talking about. Okay. Now the equation I want to solve is to be parallel, I need 0 to equal the covariant derivative along the curve of V. This is the defining characteristic. I need that to be 0. So right now what I have to do is I have to show that there exists some theta of t, right? Some theta defined along the curve, so that this is 0. Okay. Well, now we have to do the product rule. So we're taking the derivative along alpha prime, along the curve. Now, what is this going to be? Well, I want to point out again that the taking the derivative along the curve here is also d dt, okay? When you're thinking of something as a function of t, you think of it, you do d dt. When you think of it as a function of x, y, and z, or just on your surface, you think covariant derivative. So those things are really the same thing. And we have to do the product rule. So how do I take the derivative of this? Well, that's just the product rule. It's going to be negative sine theta times theta prime of t. How do I take the derivative of this? Well, that's what this omega 2,1 thing was about. That's what this is. Right? And so, and remember, just to remind you, right? This is your multivariable calculus derivative, but when you look at just the tangential part, that's the intrinsic covariant derivative that we're talking about today. And that's what's in the definition of being a parallel vector field, that the intrinsic covariant derivative is 0. Okay. So what we get then is, using the product rule here, we get minus sine theta times theta prime of t times E1, and then plus cosine theta times the covariant derivative alpha 1 of E1, right? Plus the similar term over there. And so what this equals then is minus, so let's factor out the theta prime of t. And then that will be a group of terms, right? And then plus well, sorry. Maybe over spring break I got worse at my teaching. It's possible. Am I out of practice? It's possible. Main thing is you guys still understand, okay? Like, should I remember going dot, dot, dot. You shouldn't do that, right? Plus, derivative of sine theta is cosine theta, right? times theta prime of t, E2. And then plus sine theta times the covariant derivative along alpha prime of E2. Is that right? So we just have a little bit of a calculation to do here. Okay, and so we have minus, and I'm going to use the eraser method because I'm a little shorter on board space here. I just want, does anyone have any questions before I erase a term? By the way, the eraser method is almost always a mistake pedagogically, but I'm going to do it anyway, okay? It's in the book. This right here is omega 2,1 of alpha prime E2. You all see that? So I'm just going to erase this right here and then put in omega 2,1 of alpha prime times E2, okay? And this right here, the derivative of E2, is negative omega 2,1. So I put a minus sign here. Minus sine theta. Omega 2,1 times E1. Okay? Now you'll notice that we have 4 terms there. And it turns out what this equals is, let's look at let's group the E1 terms. Okay, we got an E1 term here, and we have an E1 term there. And notice they both have a sine theta in it as well. And so what you have then is, when we factor it out, we get I'm going to factor out the minus sign as well. They both have a minus sign. And then I'm going to put in the omega 2,1 of alpha prime plus theta prime of t here. And then we have the sine theta times E1. Okay? So we have a sine theta E1 that I factored out, the minus sign I factored out, and then minus sine theta E1, and this is what we're combining those terms, right? And then we have another term, which is plus, and then we'll go ahead and collect the E2 terms over here. And those E2 terms, right, these are these 2 terms, I'm underlining them twice, okay? And they both have an E2, but they also both have a cosine theta. And then they have omega 2,1 again. And then also a theta prime. And so in fact, you get that same factor twice. And so you can say this whole thing equals 0 if, what do we need for the whole thing to equal 0? The whole thing equals 0 if theta prime of t is equal to negative omega 2,1 of alpha prime of t. And so you just simply choose your theta so that theta prime of t is equal to that. It's solving an ordinary differential equation. And that gives you the correct answer. And then therefore, if you simply choose theta of t to solve this ordinary differential equation, then the covariant derivative of v is 0. Okay. All right, question, yes.
How do you know for sure that you can choose a particular t that solves the differential equation?
Okay, good question. You're not letting me slide by, right? Just say, well, trying to use the any idiot can see that, or any fool can, which is how you know someone is skipping arguments, right? Yeah, this is, you do have to make some assumptions about your omega 2,1. But for example, if this omega 2,1 is smooth and in particular that means it's bounded, then there's a standard ODE theory that would tell you you can just integrate it. In fact, I just need a space on the board here. I guess I will erase this board. Talking about parallel vector fields. Erase this, how about that? So the last line of the proof is you simply say theta of t is equal to whatever theta is originally, and then minus the integral 0 to t of omega 2(1) of alpha prime of t dt. Okay. And so what you can see is as long as this is reasonable regularity where this integral makes sense, right? Then you can see that theta prime of t then, by the fundamental theorem of calculus, equals negative omega 2(1). And so
the existence theorem of ODEs, right?
this is just the fundamental theorem of calculus. It's even simpler than existence of ODEs. Because it looks complicated, but it's sort of like we're just saying the derivative of this is some other function, right? We know this exactly. It doesn't depend on theta, actually, right? So it's technically an ODE, but really it's just saying the derivative of theta of t is this other function of t. So just integrate it. And there you go. That's integrating it. And you can integrate, any function with reasonable regularity. And we're assuming everything is smooth, so that's not an issue. Okay. Other questions? Okay.
Is there like some significance to that final line? Like, what does theta prime of t equals? Yeah, what does that actually like mean in context?
Well, of course, the main thing is it makes this 0 and that 0, so the whole
Yeah.
thing is 0. But you're asking me for what is it, like on a deeper level, what does it mean, right?
Yes.
Yeah, okay. I'll give it a shot. What was omega 2(1)? Omega 2(1) was how much E1 was rotating with respect to E2, right?
Yeah.
I mean, let's put it this way. Had this been 0, or if omega 2(1) is 0, right, then that means E1 is sort of parallel vector field. Let's say it was 0 everywhere, right?
Yeah.
Now the problem is we know it's with our spherical example where you start at the North Pole, go to the equator, and make a triangle, right? We know that you can't have parallel vector fields in general, right? So whereas it would be nice to choose E1, E2 to where omega 2(1) was 0 everywhere, that's not possible in general. All right, so we're kind of stuck with the fact that omega 2(1) is going to be non-zero some of the time, right? But nevertheless, what it says is as you go along the curve alpha, this is telling you how much E1 is rotating. And so what this is saying is, since where's my definition of V? V is right here, right? It's saying take the E1, which by the way is rotating that much, and theta is how much you've rotated off of E1, and it's saying however much E1 is rotating, do the opposite amount of rotation with respect to E1, so it averages out to where you're not rotating at all.
Yes.
So it does make sense. Okay. Yeah, it's a good question. Good question. By the way, geodesics. Here's another theorem. Is this see, I don't see it as it's an exercise. 633, exercise 6.3.3. I'm not sure if it's in your homework or not, but the velocity vector of geodesics is parallel along the geodesics. Okay, so proof. The definition of a geodesic. Did I give a definition of a geodesic? A geodesic curve? I don't.
Yes.
I did? Okay. So it's funny how it's super regular. It's only 1 week, but even I'm rusty, so you guys must be too, right? So, but the definition of a geodesic is that if you take the covariant derivative along the geodesic of its velocity vector, that's 0. But that's also by the way, we're looking at the intrinsic derivative. Like you get rid of the third dimension, right? But that's also the definition of a parallel vector field. Right? so it's saying that this vector field here is parallel. So that's one line, one state. That's like a pretty short proof, right? This is a definition. Yes.
So how can you take the covariant derivative of a velocity vector in the direction in which it's going? I guess, like, actually, now I see why that equals 0. Never mind.
Okay. By the way, we could, this also equals the tangential part, right, of, by definition, the R3 derivative of alpha prime of t. Right, so that's what this means by definition, right? And then by multivariable calculus, what this is on the right, this actually is, when you change variables, alpha double prime of t. That's ddt of alpha prime of t. So it's the tangential part of alpha double prime of t, right? So maybe this is the and so this is saying that when a geodesic, all of its acceleration is in the direction you can't control, right? It's all of its accelerations in the normal direction, having to do with stuff that the ant is oblivious to, doesn't control, right? You're not turning to the left, you're not turning to the right, you're not speeding up, you're not slowing down, right? You're walking in a straight line at a constant velocity. And then this gives us to exercise 6.3.4, which I think is in your homework. And I think I can erase this board now. But I hesitate to, because that means for sure I'm going to need it later, right? But
Christmas theory.
I think y'all can remember this. We derived this. We have this orthonormal frame here, right? We have the E1, E2 were in principle defined by coordinates, right? Okay, so this was, maybe I just copy this over here, that you had xu over the square root of E xv divided by the square root of g u, right, that this equaled what we're calling E1, E2, and U. Okay. So we're assuming f equals 0.
Does the literature on this like actually use omega 2,1? It seems like it's the only coefficient that's kind of relevant of the omegas. So
Yeah. Yeah, that's kind of standard.
okay.
The book does it, and yeah, it's kind of
Are
standard.
there any like weird topology cases or something where like omega 1,1 isn't 0 or 1,2 and 2,1 aren't equal?
No.
Oh, that's okay.
No, there's 2 omega 2,1. It's a hangover, right?
Yeah.
And so it seems a little weird, but this omega 2,1, yeah, it's only, we ignore omega 1,2, it's just the negative of omega 1,1, omega 2,2 or 0. So it's like, why do we have all these indices now, right? You don't really have to, but maybe it reminds you where it comes from.
Okay.
Right? It's the rate of change of E1 in the direction of E2. And so what we're going to do now is we're going to, this is your exercise, and you guys figure this out yourself. It's actually a critical exercise for the Gauss-Bonnet theorem. And it's to show that the geodesic curvature of a curve is equal to d theta dt plus omega 2,1. When your curve, let's say when alpha of t is unit speed. So this is alpha 2,1 of alpha prime of t. And we define alpha prime of t to equal cosine theta E1 plus sine theta D2. Okay. So we want to prove that, okay? We want to prove this identity here. Because, geodesic curvature, we remember what geodesic curvature is, right? It's how much you're curving. You're curving it's 0 when you're a geodesic if you're going straight, right? Otherwise, it's how much you're curving to the left, I guess you might say. And so in other words, if we have this orthonormal frame E1, E2, which came from our coordinate chart defined in a disk, And then we express our alpha prime of t in terms of the E1, E2 frame, right? Because it's unit speed, that means alpha prime of t is a unit vector. And so it's some rotation of E1, and we rotate by theta. So this is how we define theta of t, right? Theta of t is how much you rotate E1 to get your alpha prime of t. This omega 2,1 tells you how much your E1 is rotating. Right? And so it's kind of obvious when you think about it. Your geodesic curvature, it's how much E1 is rotating plus how much your curve is rotating with respect to E1. This is adding up these two components. Okay, so this intuitively makes sense. We agree? This is how much E1 is rotating as you go along the curve. And then this is how much you're rotating with respect to E1 as you go along the curve. And you add it up, and that's the total rotation, and that's what we think of as geodesic curvature, right? But now let's do a proof of this, with the equation. And you guys, this is in your homework, so you can perfect it. What we have to do is we look at, let's compute the derivative along the curve of alpha prime of t. Now we already did this. We did it right here. Just replace v with, but wherever you see a v, put an alpha prime. Remember, v was also exactly the same expression. You all see that? So wherever you see a v, just think of it as your alpha prime. And so what you get is exactly the same expression here, which thank God I did not erase. I'm going to pretend like I remembered that was the right thing to do. I had a sense I should not erase that. Right? But I have to say I did not specifically remember. Okay. And so what this equals then is you can actually just factor out, let's just factor out that term here. Change the order. It's d theta dt plus omega 2,1 of alpha prime of t. And then guess what? I can factor it out, and then what I've left is negative sine theta E1 plus cosine theta E2. You guys agree? That's just the calculation we did before. Okay, so if we express a vector field, in this case alpha prime of t, in terms of E1, E2, and rotating by theta, right, as we did here, when you then take the covariant derivative along alpha prime, then you get this expression. Okay, and then you stare at this a bit, and you're trying to make sense of what is this? What is that? In other words, let's say this is E1 here, and this is E2 here. Well, if you rotate by theta, right, let's say theta is like 20 degrees, then this is alpha prime of t, right? And then we're in the surface here. The chalkboard is the surface of some surface, right? U is pointing out this way, right? This alpha prime is also called t, right? And then the question is, what is that vector? Well, this is the 90-degree rotation of t, isn't it? It's this vector here, right? Because it's negative sine theta, cosine theta. If I take the dot product of this with that, it's 0, right? I get negative cosine sine plus cosine sine. This vector is perpendicular to alpha prime of t, and in fact, it's the 90-degree rotation clockwise. And u's coming out of the board, isn't it? And so, if u's coming out of the board with that convention, u cross t, that's u cross t. So let's take the u coming out of the board, so that rotating to the left here is u cross t. Okay, so this is equal to this expression here, d theta dt, plus omega 2,1 of alpha prime of t u cross t. But wait a second. Do y'all remember the definition of geodesic curvature? The definition of geodesic curvature was you look at this, and whatever the coefficient is on the u cross t, that's geodesic curvature. So what we therefore have is, the thing in brackets is geodesic curvature, and that's what we had to prove. it's just that same calculation. And like I said, it makes sense. It's saying like the total amount you're curving, it's how much the frame is curving along the curve, the E1, E2 frame, plus how much you're curving in addition to that. Okay. Now, questions before I start erasing?
Did you mean to put a subscript under
Yeah.
the alpha? Probably not. In the circle. Yeah. Okay. Right.
That's what I meant. Thank you. Other comments, questions, corrections? Thank you. Well done. Okay. Now let me tell you what I think is the coolest thing in all this. Because, I mean, a lot of this is kind of like, whatever, who cares? Not really, kind of like exploring ideas, right? But here's something just undeniably amazing. I mean, if you're not already amazed, you could be already amazed. But I want to tell you something undeniably amazing. Is let's integrate this formula. Let's integrate it. Okay, so you have some surface here. We've got some coordinate chart. Remember, it's a coordinate chart, so it has to be a rectangle. All right, you can't have any topology in here. And so what I want to do then is take a curve that bounds a disk. We'll call this disk D. Okay, the boundary of the disk will be parametrized by alpha prime of t. Okay, and what we have is that geodesic curvature is equal to d theta dt plus omega 2(1) of alpha prime of t. Okay? Integrate both sides along the curve. Go around once. Then you get the integral around the boundary of D of the geodesic curvature times ds. ds is the thing, well, I could say d. I just like s when it's arc length, okay? But s is also t here, because remember we're saying this is a unit speed curve. Okay, so I'm going to go ahead and use s here. S equals t, okay? Because it's a unit speed curve. This term here is the integral of theta prime of t times dt. Well, what is the integral of d theta dt times dt? Well, this is just, if I go from a to b, right, this is just going to be theta of b minus theta of a, right? That's what you get when you integrate fundamental theorem of calculus. And you might say, oh, okay, but whatever theta is here is also the theta there, right? But you'd be wrong. Because why? Theta increased by exactly 2 pi. You went around once, right? If you started at angle 30, you went to 390, right? But you went around once. And so this equals 2 pi. And then we have plus the integral over the boundary of D of this thing, omega 2(1) of alpha prime of t, dt. Okay? And again, t equals s, so you can put an s there if you like. I'll just say this, t equals s, okay? So I don't know, I prefer to put s because, don't you guys use s for integrating boundary terms, right? It's typical, it's conventional. Again, multivariable calculus, you get integral of ds gives you the length of the curve, right? Okay. Turns out you can apply Green's theorem to this. And what Green's theorem, you don't even have to remember the details. Remember Green's theorem says the integral around the boundary is equal to the integral over the interior. It turns it into a double integral. And so you get an identity. And the identity you get let's put it to the other side here. It's going to be some sort of double integral over d. Okay, so it turns out that you can apply Green's theorem to that. Now that's not obvious. But you can. And maybe, wait, what is obvious? Let's just think about it. What is obvious? Is this obvious? Because it's like usually what Green's theorem is, you have like the flux of a vector field kind of thing, or actually it's the path integral of a vector field, right? So you have to be able to extend this to the inside, and it's not immediately obvious what that is. Okay? So it's not obvious. I want to say it's not obvious that you can apply Green's theorem to this. Not obvious, okay? Not obvious. But it is remarkable that you can. And when you do that, it turns out what you get over here is the integral of the Gauss curvature times the area form. Boom. There you go. Gauss-Bonnet formula. Magical. Gauss called this his remarkable theorem, right? When Gauss is impressed, you know it's good. Okay? And so what you have is that the integral over that disk of the Gauss curvature of the disk, the intrinsic geometry here, plus the integral of the geodesic curvature along the boundary, this always equals 2 pi. This is Gauss's theorem for a disk. And if you don't like that, then get out. Okay, that's too aggressive, right? Now, then, okay, if you don't like that, then I'm sorry, you probably took the wrong class. I don't know. That's just really cool. Gauss's theorem on a disk. Amazing. On the other hand, beautiful. It's like this might be, I mean, it's on my short list of favorite theorems of all time. Right? And Gauss liked it, and you know what? Who are we to argue with Gauss? This is super cool. Okay? And just to point out, two examples of this. And by the way, right now this is the theorem for a disk. All the other versions of Gauss's theorem can be proved from this theorem. Okay, so understanding this is like definitely the first step. But for example, imagine you have half a sphere, right? And I always like to do these two examples. You take half a sphere. Now erase the bottom half of the sphere, right? In this case, you have the geodesic curvature is 0 along the equator, right? And the Gauss curvature here is equal to 1 over r squared, where r is the radius of the sphere, right? And then sure enough, what's the surface area? Remember, it's 4 pi r squared. So it's 2 pi r squared for half a sphere. 2 pi r squared times 1 over r squared. Boom, you get your 2 pi, that's 0, right? On the other hand, imagine you have a flat disk, right? Of radius r. Here, these both will have radius r. Here, the Gauss curvature is 0, and the geodesic curvature, we recall, is 1 over r. That's 0, integral of 1 over r times 2 pi r, 2 pi again. But it's not just true for a disk, it's flat, it's not just true for, it's any geometry you could possibly put on a disk, this will always be 2 pi. Now, how do we prove this, just for the record? Because we'll do it tomorrow. I mean, Wednesday. We'll finish it Wednesday. How do you prove this? A bunch of EF and G calculations. Remember how we have a formula for the geodesic curvature in terms of a bunch of EF and Gs? Okay, so effectively, we can compute this in terms of EF and Gs, apply Green's theorem to it, and you get a bunch of stuff in terms of EF and Gs that just so happens equals the Gauss curvature. Okay. And so really there isn't anything else for me to explain sort of conceptually. Right, now it comes down to formulas. And it's just sort of remarkable that this actually does work out. And I like the questions y'all ask me. Y'all been asking good questions today. Evan, you made me think a bit. And why should this be true? Like, I mean, that's a great question. It's like, is this obvious? Is this, of course, is this like you're supposed to have an aha moment where you're like, oh yeah, of course, Gauss-Bonnet theorem. I'm still working on that. I'm 53 years old. I'm a differential geometer. Yeah, I think I could make the case for it, but I'm still working on it. I have not perfected it. And so maybe we can discuss that a little bit next time too. Right, but I think these two examples show something. I mean, it's just, I'm going to say here's the extent to which it's quite surprising. There's really is content here because guess what? This isn't true in 3 dimensions. Like this is true for surfaces. Like you go up 1 dimension and try to do something that's true for, no, sorry. They have things they call Gauss-Bonnet formulas in dimensions 4 and higher, but they're not really Gauss-Bonnet formulas. They're cool. I guess it's fine. They can call them that if they want. But this is really a 2-dimensional phenomenon to have it quite this simple and quite this beautiful. And so what's really telling you, what's captured in here, is that curvature is fundamentally a 2-dimensional phenomenon. There's something special about 2 dimensions. Curvature is 2-dimensional. When you try to understand curvature in higher dimensions, it's all based on your intuition for 2 dimensions. Okay. Good to see y'all. Good luck on your homework due Friday. And I think we're kind of winding down, right? So try to get an early start on your homework and ask me questions next time.